You finish writing a novel today. 5 years from now, you want to prove this exact date. You don't need to publish the manuscript. Just engrave its fingerprint somewhere no one can tamper with. Bitcoin's blockchain is perfect for that. But Bitcoin was built for money, not data. So how do you slip a fingerprint into a financial ledger without the network resenting you? Developers love Bitcoin for non-payment use cases because it offers three things at once: a global timestamp, immutability, and the verifiability from anywhere. Drop a SHA-256 hash, a 32-byte fingerprint of your document into a block, and you've notarized it. Anyone forever can confirm that document existed by the time of that block. The blockchain becomes a worldwide notary public. The catch: every byte you add is a cost shared by every full node. Meet the UTXO set. UTXO means unspent transaction output, every coin that hasn't been spent yet. A full node, which is any computer that independently validates the entire chain, keeps this set in fast memory. When a new transaction arrives, the node must instantly check whether the inputs exist and are unspent, so the UTXO set lives in RAM. Every output you add stays there until it's spent. Bloat the set and you raise the hardware cost of running a node for everyone. Before OP return, developers had a hack. Bitcoin addresses are just numbers. So they crafted fake addresses by stuffing their data into the address field, then sent a tiny payment to it. The output looked like a normal payment. The network couldn't tell it was fake, but no private key existed for that address. Nobody could ever spend it. So the output sat in the UTXO set forever, consuming RAM in every full node on Earth. This was the original sin: permanent, unspendable bloat disguised as payment. OP return is the negotiated answer. It's an opcode, an instruction in Bitcoin's scripting language, that when placed at the start of an output script, immediately halts execution and returns false. Any future transaction trying to spend this output runs the script, hits OP return, fails, and gets rejected. The output is provably unspendable the moment it's created. Nodes can detect this at parse time and skip adding it to the UTXO set entirely. Here's the anatomy of a real OP return output. First byte, the OP return opcode itself. Next, the payload. Take proof of existence, an early notarization service. Its payload begins with 8 ASCII bytes, spelling DOCPROOF, a magic prefix that lets anyone scanning the chain identify these notarizations. After that comes a 32-byte SHA-256 hash of the document being timestamped. The output's value is 0 satoshis. No Bitcoin is attached, because any coin sent here will be permanently destroyed. The transaction still pays a fee to the miner, but nothing of value gets locked into an unspendable script. Watch what happens if someone tries to spend an OP return output. They craft a transaction referencing it as an input. Their node feeds the locking script into the script engine. The engine reads the very first opcode. OP return halts immediately and pushes false onto the stack. Validation fails. The transaction is marked invalid and rejected before it ever reaches a mempool. This isn't about lost keys or weak signatures. The unspendability is mechanical. The script engine itself refuses to proceed. There's no clever workaround. 3 misconceptions was killing. First, op return is not free. The transaction still occupies blockchain space and still pays miner fees. The savings are specifically to the UTXO set, not to disk or bandwidth. Second, op return outputs cannot be unlocked with the right key. There is no key. Failure is built into the script. Third, this is not cloud storage. Standard Bitcoin relay policy caps. OP return payloads historically at 80 bytes, enough for a hash and a small prefix, nothing more. OP return is a microcosm of Bitcoin governance. Purists wanted the chain to do one thing well. Builders saw a global timestamping service waiting to be used. Rather than ban data outright, the protocol carved a narrow, well-behaved channel. Data lives on disk, never in working memory, and signals its uselessness to the engine before it touches state. Today's notarization services, metadata protocols, and the precursors of colored coins all ride this compromise. It's the reason your laptop full node still fits comfortably in RAM.